In this tutorial, I will explain the features of the graphic user interface of MULTEM through a series of practical examples step by step. MULTEM is an open source software performing transmission electron microscopy image simulations for different experiments as high-resolution TEM, STM, ISTEM, electron diffraction, precession electron diffraction, convergent beam electron diffraction, annular dark field TEM, annular bright field holocone, EFTEM, and ILS. I developed this software during my PhD and my first year as a postdoc at EMAT. As we go along with this tutorial, we will run some examples to experience the effects of different parameters on the simulation. MULTEM software can be found on the following link. After clicking this link, it will open the following website, in which you will find a description of the software as well as the required steps for using the Windows precompiled UI interface and Makefile for MATLAB. Besides, there is a description of the necessary steps for building MULTEM for MATLAB in Windows and Linux. Keep in mind that this step works using MATLAB 2020b and CUDA 10. It assumes that Visual Studio 2017 Community, G++ 7.5 or Clang Xcode 10 compiler is installed in your operating system. Additionally, MULTEM also requires installation of the FFTW3, BLAST, and LACPACK libraries. If you use MULTEM in your publication, please cite the following papers. If you also use the hydrogenic electron scattering factor, please cite this paper. In addition, there are two books I would like to recommend for everyone who wants to get a better understanding of transmission electron microscopy. The first one is the Introduction to Conventional Transmission Electron Microscopy from Marty Graf, in which you will get an overview of the TN and its principles. However, if you really want to go into modeling the electron-specimen interaction, then I definitely recommend you Advanced Computing Electron Microscopy from R. Kirkland. With this book, you will get a profound understanding of the numerical method to model the electron-specimen interaction and the imaging process. The webinar will follow the PDF tutorial, which can be found in the MULTEM GitHub repository inside the tutorial folder. Moreover, we will use the release version MULTEM 2.23, which contain the precompiled binary files. We do this by clicking on the release link and then click on the MULTEM stable zip file. After downloading and compressing the file, you will find a list of folders. Look for the folder name GUI bin, open it. This folder also contains a subfolder named specimen, which contains all the specimen files that you will need in this tutorial. In the main folder, you will also find a folder with the name examples MULTEM, which contains MATLAB scripts to run the MULTEM software through MATLAB. The same setting that can be changed in the graphical user interface can also be changed in these scripts. However, we won't focus on the MATLAB scripts this time. To start this tutorial, go back to the GUI bin folder and open the executable file MULTEM. Before starting this tutorial, we would like to answer a quite important question. Why do we need simulation? To answer this question, here is a schematic drawing of the electron microscope. In the first part, we have the electron source, electromagnetic lens system, the sample holder, and the imaging system. The most important part of this drawing is here when the electron interacts with the sample. Because this interaction is almost 3 orders of magnitude larger than the photon specimen interaction, and all the quantum mechanical effects get stronger, that requires that the experimental data must be compared and complemented by numerical simulation. As example of this is high-resolution TN of strontium titanium O3 along the 1-1 orientation. We can see here the experimental one. In order to validate that its data represent something that we know like a projected structure, we have to validate it with the simulation. But also simulation can help you to extract more quantitative information from experimental data. In this case, we have a HDAF STEM image, and combining with something called scattering cross-section from simulation, we can convert these intensities of scattering cross-section to number of atoms. Now that we know the reason for using simulations, the next question will be how to perform accurate and fast simulations. When the electron interacts with the sample, we can divide this interaction in several types. We can have elastic scattering electrons, OE electrons, secondary electrons, and so on. Here we're only going to focus on elastic scattering electrons and diffracted beam in elastic scattering electrons, but only coming from phonons. This interaction can be described by using the paraxial approximation of the Schrödinger equation. This equation can be solved by using general methods like a Runge-Kutta order form. However, the most popular method to solve this equation are based on the multislice method and the Bloch method. Looking at this equation, the only unknown parameter is the BR. So the BR is the specimen potential. This potential can be approximated by using the independent atom model or by using first principle based on DFT calculations. If we want to perform accurate simulation, then we have to use high order expansion of the multislice solution of the paraxial approximation of the Schrödinger equation, accurate electron scattering parametrizations, correct slicing of the three-dimensional atomic potential, frozen phonon, frozen atom calculation, and proper inclusion of the microscope's aberrations. If we want to perform fast simulation, we have to use the current available technology, as the GPU technology, multi-threading technology. Apart from that, we have to use a suitable programming language which allows you to get the best of your hardware. In this case, we use C++ and CUDA C++. Using this programming language, you can write high-level C++ library or a wrapper for MATLAB, and even you can go further, you can write a graphic user interface to make it available for experimental people. The graphical user interface of MULTEM consists of 4 separate panels: general settings, specimens, experiments, and microscope settings. Initially, some default settings are already pre-filled. In each panel, the information required to set up your image simulation can be changed in intuitive order. When you hover over a parameter of any of these windows, an information box will appear. The same explanation for the parameter is also shown at the lower left bottom of the interface. You can start the simulation with the green start button and stop it with the red stop button. The result of your simulation will appear on the new window. All the results can be saved as TIFF images of binary format file by right-clicking on the image. Furthermore, we can always return to the default values of MULTEM by clicking on the circular arrow. In this tutorial, we will walk through some possibilities of MULTEM has to offer for STM and TM image simulation. You may notice that some options are disabled, that this option might be available in the future releases of MULTEM program. Through this tutorial, all exercises will start from the default values. Finally, we are ready to start with the MULTEM tutorial. To do that, we go into the MULTEM folder and open the file name MULTEM Image Simulation Software Worksheet PDF file. And then we go to the page number 2 for the first exercise. In this exercise, we will study the effect of the acceleration voltage on the incident wave on real space. So most of the exercises in this tutorial consist of 2 parts: the setting up for the exercise and the exercise itself. So let us start. We're starting by setting the default values, and then we select into the experimental panel the incident wave real space. We go to the microscope setting and change acceleration voltage to 80 kiloelectron volts. Now we go to the exercise and we have to run the simulation. We have to leave the image open and change the acceleration voltage to 300 kiloelectron volts and rerun the experiment. Now in this part we also have to answer some questions. Those images show the results of our simulations, in which we can clearly see that the probe size at 80 kiloelectron volts is broader compared to the probe size at 300 kiloelectron volts. This is due to the probe size is directly proportional to the wavelength. With decreasing the acceleration voltage, the energy decreases and the wavelength increases. The broader profile and larger wavelength practically reduce the resolution in the STM images. In this exercise, we will study the effects of the aberration on the incident wave in real space. For convergent beam probe, we can control this aberration with the condenser lens panels, in which we have access to the symmetrical aberration as spherical aberration order 3 and spherical aberration order 5, as well as the focus. You also have access to the non-symmetrical aberrations as a twofold astigmatism and so on. To start the exercise, we set the defocus value to -100 Angstroms and run the simulation. We leave the image open and change the defocus value to 100 Angstrom. Rerun the simulation. As a final step, we use the optimize defocus by pressing this optimize button. It's going to use the cursor defocus and rerun the simulation. Here we have the results of our simulation for a defocus value minus 100 Angstrom, cursor defocus, and 100 Angstroms. Aberrations are modeled by means of the contrast transfer function of the objective or condenser lens, named here H0. This describes the aberration of the objective lens in high-resolution TN and specifies how the condenser system shapes the probe in STM mode. Ideally, a lens for spherical wave converging on or emerging from a single point. In practice, aberration causes the wavefront to deviate from the spherical surface. This deviation can be represented as a phase error chi or the spatial frequency in polar coordinate, which can be written as a series of expansions. Due to the fact that we start all our simulations from the default setting values, all aberration coefficients have 0 values, but C3, which has a value of 1 micrometer. Generally speaking, smaller aberration allows for a smaller probe and therefore a better resolution. As we can see from our simulation results, different defocus values give you different probe sizes. The sharper probe as possible for a given set of aberrations have to be obtained by minimizing this equation. However, if you only have a C3 aberration, then the optimal defocus value which minimizes this part of the equation and gives you the sharpest probe is called cursor defocus, which in this case is minus 14 Angstroms. In the second part of this exercise, we will study the effect of the spherical aberration on the incident wave on real space. We start by setting the default values and changing the simulation type to incident wave real space. We also set the spherical aberration to 0.1 millimeter. We optimize the defocus to cursor and run the simulation. We leave the image open, change the defocus value to 0.1 millimeter, run the simulation, and finally we use the optimize defocus and rerun the simulation. Spherical aberration is a rotational symmetric aberration as it can be seen in our simulation results. Generally speaking, large spherical aberration produces larger probe sizes. However, it can be partially compensated by using the optimized cursor defocus. At this stage of the tutorial, we will study the effects of symmetrical aberrations on the incident wave on real space. We start by studying the effect of the two-fold astigmatism. Start by setting the default values, choose the incident wave real space, unfold the non-symmetrical aberration, and change the modulus of the two-fold astigmatism to 20. Run the experiment. Then we also set the azimuthal angle of the two-fold astigmatism to 45 degrees and rerun the experiment. From our simulation result, we can see the effects of the two-fold astigmatisms on the incident wave on real space in both the modulo and its phase. Due to the fact it is not a symmetrical aberration, it is quite dependent of the orientation or azimuthal angle. In the fourth part of this exercise, we will study the effect of the threefold astigmatism on the incident wave. We start by setting the default values, going to the experimental panel and choosing incident wave on real space. Then we move to the microscope settings and change the threefold astigmatism to 5000 Angstroms and run the simulation. From our simulation results, we can see the characteristic threefold symmetry of this aberration in both its modulo and phase of the incident wave. The effect of axial comma is studied in the fifth part of this exercise. Let's start from the default values, choose incident wave real space, unfold the non-symmetrical aberration, and choose the axial comma. We set the modulo of the axial comma to 25,000 Angstrom and run the simulation. Our simulation results show the characteristic elongation shape of the axial comma. Keep in mind that this is a second-order aberration which can be easily compensated in modern microscopes. MULTEM also allows you to add an aperture before the lens. The inner and outer radius of this aperture can be entered in millirods. In the exercise number 3, we will study the effects of the outer aperture radius on the incident beam. So to start the simulation, we set up the default values and change the experiment to the incident wave real space. Now we will run our simulation for 3 different aperture radius. Start from 7 millirads, then change to 21 millirads and 50 millirads. Now we will do the same, but including a small two-fold astigmatism of 20 Angstrom. So we start with 7 millirads, 21 millirads, and 50 millirads. From our simulation results, we can conclude that the largest possible outer aperture radius would be desirable for symmetric aberrations as the probe becomes smaller and smaller. This can be seen in the first row. However, a larger outer aperture radius also means that higher scattering angles contribute to the signal, which are influenced by the aberration a lot stronger. In practice, aberration cannot be fully admitted or corrected, which means that increasing the outer aperture is always a trade-off for accentuation of aberration effects. Hence, the outer aperture radius cannot be chosen arbitrarily large, but is limited by the microscope aberrations. These effects can be seen in the second row. In this exercise, we will study the effects of the aperture inner radius on this beam. We start our exercise by setting the default values and changing the simulation type to incident wave real space. We set the inner aperture radius equal to 18 and the defocus value to 0. Run the simulation. Now we change the defocus value to -50 Angstrom and rerun the simulation. Finally, we repeat it, but for a defocus value of 50 Angstrom. Blocking the central part of the electron beam via inner apertures creates the so-called bezel beam, which changes phase according to the bezel function. The biggest advantage of the bezel beam is that it's very stable to the focusing, as can be seen from our simulation experiments. However, a large fraction of intensity is lost using an inner aperture. In order to have a better understanding of the bezel beam, we can compare it against the convergent beam, in which the intensity of the beam varies strongly against the defocus values. However, in the case of the bezel beam, that intensity is rather constant over a large range of defocus. In the exercise number 5, we will study the effects of the momentum of the vortex beam. We start this experiment by setting the default values, changing to the incident wave real space, and setting the vortex momentum equal 0, running the simulation, then changing to 1, and finally repeating the same for m equal 2. From our simulation result, we can see that the orbital angular momentum show a radial symmetry for m equals 0. However, for m equal or bigger than 1, it shows a symmetry on the phase. Besides, it shows the characteristic donut-like shape on its modulus. It's time to introduce a sample in our simulations. For speed, we will work with the simulation type exit wave from real space. When we introduce a sample into the simulation, we have to describe the electron-specimen interaction. One of the best descriptions of electron-specimen interaction is based on the multislice approach, which is also computationally efficient. In this approach, the specimen is divided in several slices, and at each slice, the predicted potential is calculated, from which the transmission function is obtained. Then the transmission function is multiplied by the incident beam, and it is further propagated to the next slice. This whole process is repeated for all slices within the specimen. If we neglect this propagation within the specimen, that is the so-called phase-object approximation, which is entirely based on projected the potential of the specimen. A first Taylor expansion of this expression is called the weak phase-object approximation. In this exercise, we will study the effects of different descriptions of electron-specimen interaction. So we start by setting the default values and loading the specimen copper O1 electron-specimen interaction. Then we run the simulation. We leave the image open and change the specimen interaction to weak phase object and rerun it. Finally, we use the last option, which is based on the phase object approximation. However, the image intensity under the phase object approximation shows randomness values, which at first glance is surprising. But we have to remember that under this approximation, all interaction is carried on the phase, which can be visualized if we show the phase of the wave function. This equation also tells us that we should expect a constant value of 1 for the model of the wave function, which it is. However, all these artifacts arise due to the use of the rescaling process. In reality, the difference between those values are of the order of 10 to minus 16, which is due to the use of the floating point in our calculations. For this exercise, we can see that multislice approximation with a weak phase object approximation show the expected results, which is high resolution 10 images for a FCC crystal along the O1 orientation. As an extra information, MULTEM also allows you to use different electron scattering parametrizations. Some of them are Gaussian-based, as a Doyle-Turner and Penn parametrization. However, Kirkland parametrization uses a basis composed of Gaussian plus Lorentzian. On the other hand, Bike-Meyer parametrization uses a different base, which is 1 minus a Gaussian over G squared. Or you can also use our current available parametrization, which is based on the hydrogenic model. If we want to perform realistic simulation, we have to include electron-phonon interaction. MULTEM allows you to include this interaction under the frozen phonon approximation, in which, due to the fast speed of the electron, which can travel a few nanometer thick of the sample in the order of femtoseconds, and due to the large scale in time of the phonon vibration, which is normally in the order of few picoseconds, we can safely assume that each electron will see a different configuration at each time. Finally, what we measure is going to be the average intensity of our wave function. In the exercise number 7, we will study the effect of the inclusion of electron-phonon interaction in our simulations. We start by setting the default values and then changing the electron-phonon interaction to a steel atom approximation, loading the specimen silver O1 electron-phonon interaction. We run this experiment. Then we change the electron-phonon interaction to frozen phonon approximation and change the number of configuration to 1. We run the experiment and then we change the number of configurations to 5. Run it again. Finally, we change the number of configuration to 20. Here are the results of our simulations. In the case of steel atoms, the interference is strongly pronounced because all atoms are exactly stacked over another within the columns. However, in the case of the frozen phonon approximation, by introducing a random atomic position offset with a given probability distribution, cause a blurring as seen in the second figure. Averaging over more and more phonon configuration create increasingly smooth images and more realistic simulation as seen in the last figure. In the exercise number 8, we will study how to add vacuum in our simulation. We start by setting the default values and loading the specimen goal O1 adding vacuum. To add vacuum, we have to change the simulation box size, in this case to 50 Angstrom, and run our simulation. Then we recenter our specimen and rerun our simulation. Here are the results of our simulations without recentering and recentering the specimen. The artifact we can see at the borders of the image arises due to the use of the Fourier transform in our calculation, which implicitly requires the use of periodic boundary conditions. For an infinite crystal in the xy direction, these conditions automatically fulfill. However, for nanocrystal, this is not the case. An atom at the edge of the image is wrapping around the boundary if you don't compensate by adding vacuum around the nanocrystal. This wraparound effect still occurs in this figure, however, it only affects of region of vacuum now. Therefore, this effect does not introduce artifacts in our simulations. In the exercise number 9, we're going to study the effect of the specimen rotation in the exit wave. We start this exercise by setting the default values and loading the specimen platinum O1 rotation. We also set our rotation angle to 45 and run our simulation. The second part, we are going to change the simulation box size to 70 Angstrom in order to add vacuum, and also we recenter the specimen and rerun our simulation. A rotation of 45 degrees of the platinum crystal in 001 orientation around the 100 axis would intuitively result in the change of the zone axis orientation to 110. However, the rotation does not result in the structural repetition what would want. Instead, the first figure is actually a simulation of the nanocrystal with varying thickness and subject to the wrap around effects. Adding vacuum and recentering the specimen avoid the wrap around effects as seen in the second figure. In the exercise number 10, we will get the exit wave of a crystal at different thicknesses. We start this experiment by setting the default values and loading the specimen file name goal 01 thickness. We go into the thickness type and change from whole specimen to by thickness. We also change the thickness step to 4.078 and run our simulation. In our output window, we get access to all our simulation by different thicknesses. Furthermore, we can also change the color map, also show the coherent wave, its modular or its phase. In this exercise, we got the exit wave at each unit cell for a total thickness of around 10 nanometers. Note that this kind of simulation by thickness option only makes sense if there is a periodicity along the beam direction. Furthermore, the whole specimen is faster than by thickness because extra memory is required to store the intermediate slice solution. In exercise number 11, we will study the effects of the defocus on the exit wave, which can be done by changing the defocus itself or changing the reference from which the defocus is measured. We start this exercise by setting the default values and loading the specimen file name gold nanoparticle defocus. Then we move to the microscope setting panel and change the defocus reference to the last atom and run our simulation. Next, we change our reference defocus to first atom, rerun our simulation. And finally, we set our reference defocus to half of the thickness of the middle of the specimen. From our simulation results, we can see the effect of changing the zero defocus reference on the exit wave. In the material science community, this reference is normally set at the last atomic position. On the other hand, for biological simulation, this reference is set at the middle of the specimen. However, experimentally, this point is not exactly known. A very important part of the multislice method is the potential slicing. MULTEM offers you three different kinds of potential slicing. In the slicing by plane, the automatic periodicity along the beam directions is detected, from which the potential slicing are assigned. In slicing by DC, the user defines the slice thickness. Finally, sub-slicing by DC, the user also defines the slice thickness. However, an extra distance for all atoms that contribute to the potential within a slice is also considered. We start exercise number 12 by setting the default values and loading the specimen file name gold nanoparticle slicing. We also change the simulation box size to 70 Angstrom and recenter the specimen. We go to potential slicing and change it to slicing by DC and set the slice thickness to 2 Angstrom and run the simulation. We leave the image open for comparison and change the slice thickness to 20 Angstrom and rerun the simulation. Finally, we choose slicing by planes and run the simulation. The multislice approximation is only correct within the limit of a very small slice thickness. The relative small difference on our image simulation between the slicing by DC with a slice thickness of 2 Angstrom and slicing by planes is due to the automatic slicing is detecting a slice thickness of around 2.037 Angstrom, which is actually quite close to the slice thickness defined on slicing by DC. However, if we increase the slice thickness, some image artifacts start to appear, as shown in the second figure. As a rule of thumb, if your specimen doesn't show any periodicity along the beam direction, it's better to define our own slide thickness. On the other hand, for crystalline specimen, automatic slicing works pretty well. In the exercise number 13, we will study the potential sampling. You start by setting the default values and loading the specimen file name CalioArsenine-01 sampling. We change the potential sampling to 128 and run our simulation. We leave the image open and change our box sampling to 1024 and rerun our simulation. The potential sampling has to be good enough in order to capture all relevant details of our simulation type. If we perform a simulation by using a small number of sampling points, it will yield to unrealistic results. Increasing the number of simulation points will generate realistic images at the cost of increasing the computational time. As a rule of thumb, a pixel size of around 0.05 Angstrom will be good enough for most of your simulations. In the exercise number 14, we will generate a high-resolution transmission electron microscopy simulation. We start by setting the default values and loading the specimen file name silicon-01 high-resolution TM. We go to the thickness type and change the whole specimen to by thickness. We also set the thickness step to 5.04707 Angstrom. Then we move to the experimental panel and choose high resolution TM simulation and run the experiment. Don't forget to use the slide bar to see your results for different thicknesses. When looking at the image at different thicknesses, we notice a change in intensity at atomic positions due to the contrast reversal. As the wave propagates through the sample, the phase is being shifted further in each slice. This causes an intensity modulation along the thickness according to the phase shift with a period of 2 pi. These contrast reversals can be compensated by playing with the aberration, for example, the defocus and spherical aberration. In the exercise number 15, we will generate some electron diffraction simulations. In the first part of this exercise, we will focus on the intensity variation of the diffraction spots. We start by setting the default values and loading the specimen file name silicon-01 electron diffraction. Go to the thickness type and change it to by thickness and set the thickness step to 5.4707 Angstrom. Go to the experimental panel and choose electron diffraction and run the simulation. From our simulation results, we can see that some diffraction spots appear and disappear with varying intensity due to dynamical scattering. Furthermore, we can see some diffuse intensity between these diffraction spots, which are known as thermal diffuse scattering. This scattering arises due to the inclusion of phonons in our simulations. In the second part of this exercise, we will generate some Kikuchi lines. We start by setting the default values and loading the specimen file name goal-01 thickness. We change the thickness type to by thickness and set the thickness step to 4.78 Angstrom. Go to the experimental panel and choose electron diffraction and run the simulation. From our simulation results, we can see some higher than low zones and some distinct bands which are known as Kikuchi lines. These are easily seen in diffraction pattern of thick specimen or moderate specimen thicknesses with strong scattering power due to the multiple scattering. Kikuchi lines are formed by the thermal diffuse electrons as a result of the atomic vibration. Unlike diffraction spots which are sensitive to orientation, Kikuchi bands mark orientation space with well-defined intersections, and therefore they serve as rods in orientation space. In exercise number 16, you will learn how to perform a scanning transmission electron microscopy simulation. If you choose this mode, it will drop out 3 different menus. In the incident wave menu, you can choose between convergent wave user-defined and auto mode. However, in the case of HRTEM, the auto mode means convergent wave. If you choose the user-defined, you have to select a file name which contains a complex matrix in a binary file. You will also need to define what is your zero reference. In the scanning menu, you have to define the number of scanning points and whether you want to include the last scanning lines of your scanning pattern. For the scanning type, you can choose between line of area. In both cases, you have to choose the initial and ending scanning points. The detector part, you can choose the number of detectors and whether you want to run your simulation for ideal detector or matrix detectors. In the ideal case, you have to set what is the inner and outer angles for each detector. In the case of the matrix, you have to select a file name with your detector map sensitivity as a matrix in binary file. Now we are ready to start with our exercise. We start the simulation by setting the default values, loading the file name Angstrom-titanium 0301 STM. We change the sampling to 512 and we select the experiment STM. We change the number of scanning points to 5 and we set the scanning area to 11.715 for the initial positions, and for the end position we set it to 15.62. Then we run the simulation. We also replicate 3 times the simulation. We leave the image open and change the number of scanning points to 20 and rerun the simulation. We replicate our output result 3 times. We leave the image open and add a second detector with the inner angle of 0 and outer angle of 20 millirads. Set the number of scan points to 10 and rerun the simulation. We replicate our STEM image simulation 3 times, and by using the slide bar you can change between detectors. The first thing we notice in this exercise is that the computational time increases by a large factor compared with the previous simulations. This is due to the fact we have to repeat the full multislice process including phonons for each scanning point. The simulation time will be proportional to the number of scanning points embedded on the scanning area. Keep in mind you have to use enough sampling points in order to capture the relevant information on our experiment. In this exercise, we also learn how to perform STEM simulations with different detectors. In the first figure, we see a dark field simulation for an angular detector from 40 to 100 millirads. In the second figure, we see a bright field simulation for an angular detector from 0 to 20 millirads. Finally, we are at the last exercise of our tutorial, in which you will learn how to perform an energy filter transmission electron microscopy simulation. If you select this experimental mode, you will end up with 2 different menus. The first incident wave menu was already discussed in the STEM part. In the second menu, you have to choose the element and the energy loss for which you want to perform the experiment. You also need to choose the collection angle and the M selection rule. Finally, you also need to choose which approximation you want to base your calculation, which can be single channel approximation, mixed channel approximation, or double channeling. Now we are ready to start with our exercise. We start this exercise by setting the default values and loading the specimen file name Angstrom-titanium 01 EFTEM. We change the sampling to 512. We go to the experimental panel and choose EFTEM simulation. We choose the element strontium and the core energy loss to 1940. And we will use the approximation double channeling. We run our simulation. EFTEM allows the selective imaging of particular atom type based on their specific inner shell ionization energies. The donut shape of the image atoms makes sense physically, but is usually not observed in experiments due to practical resolution limits. We notice that the computational time for EFTEM simulation increases by a large factor compared to high-resolution TM simulation, even though both are single-shot imaging mode. This is due to the fact that the simulation time is proportionate to the number of atoms of the selected atomic type and the channeling approximation mode used in the calculation.